Okay, so if we take 896 and we divide it by 2 right away, we get 448. Oh, that's clearly divisible by 4, isn't it? Okay, so if I divide by 4, I get 112, which is still divisible by what?
At least 2.
At least 2?
4.
Right. Huh?
4.
The 4 actually works? Okay. So look up here at these factors, folks. We already pulled a 2 out. Now we've got an 8, and now the product here is 8. So 8 times 112 is this. And then you notice that 4 divides into this. So if I divide that by 4, I get down to 28. Oh, there's another 4 there. This is cleaning up quite nicely, isn't it? Times a 7, 4 times 7. So leaving that stuff very easily with your calculator, folks. If you leave that stuff there on your calculator screen and then you come back up to your paper, on the side, you could take 896 and write down that that's equal to 2 times 4 times 4 times 4 times 7. Here's the 28 right there. So if I wanted to clean up this square root, and a lot of people have trouble with radicals back in intermediate algebra, so if you wanted to clean this up and write down an exact answer, how much of this could you pull out of that square root?
3/4.
Pull out the 8.
So here's your 896 under the radical. We have 4 squared, and then notice here.
Just use the 4, break it down to 2s.
Right.
Pull out a 2.
Yeah, actually we can pull out more, can't we? You're right. Thank you. So this is a pair of 2s, pair of 2s, pair of 2s. There's 6 2s right there, aren't there? So 2 to the 6th times this other 2 times 7. So it's 2 to the 6th times 14. And so if that's a radical, then how much can you pull out? How much of this can you pull outside the radical? 2 cubed. You pull 2 cubed out of the radical, and it leaves you with 8 radical 14. Now that's a review from intermediate algebra for you. So the reason I wanted to do that is be able to review coming down to an exact answer using the quadratic formula. So let's keep going here. We have minus 14 plus or minus 8 radical 14. And would somebody check this first? If this goes back under the radical, it goes in as a what? What number? If you take 8 back under the radical, it goes back in as a, no, as a 64. If you pop it back inside the radical, doesn't it go back in as a 64? And so check 64 times 14 out. I always double check that because I easily can make a mistake in the arithmetic. So I double check that. Imagine popping a 64 back in there times 14. That does equal 896. And so here is a form of the exact answer. Is that the way we'd leave it? What would we need to do to wrap it up?
Take out a 2.
Yeah, there's a common 2 factor in the numerator and denominator. So the safe way to do that is always factor out the common factor. So get it in this format and then reduce the 2's out of there, and then there is your answer. So let me go ahead and write that before this board collapses on me. So the exact answer then is -7 plus or minus 4 square root of 14 over 7. Now, there are 2 answers here, aren't there? Let's get those approximately with our calculator. Let's get those approximately with our calculator. And watch this. I could punch that up on the calculator, but I want to run a little program, and feel free to come by the Math Resource Center and we can give you this program called Quadratic Formula. So I start this program called Quadratic Formula, and it asked me to input the A, B's, and C's. So I go back to the original problem. If I want an approximate values, A is 7, I hit enter. B is 14, hit enter. And C is negative 25, enter. And there is the discriminant, which is the item underneath the radical that we usually have trouble with. And then here are the two roots, or the two zeros of that quadratic equation. So I'm going to write those down to about 4 decimal place accuracy. So I have one answer that is a 1.1381, and the other one is approximately negative 3.1380. 1, thank you. To 4 decimal place accuracy. Any questions? Any questions from anyone? Can I assume you're with me? Okay. Now, what do you always have to do when you go down and do all this work and come up with these answers where you've taken an equation that was originally logarithmic, we removed the logarithm by writing it in exponent form, and then we used our algebra processes to finish it off? What do you always have to then do with these answers? Put them back into the original problem to see if they work. Now keep in mind, we have a 1.1 roughly and a negative 3.1. Okay? Keep those in mind because we're going to go back over here to the other board. Come back up to this original logarithm equation. If I put in the 1.1 in here, this is probably going to be just fine. Okay? I'm just going to leave it at that for the moment. But if I put the other answer, negative 3.1 in here for x, negative 3.1, I'm talking about the logarithm of a negative number here.
Can't do that.
Melissa says you can't do that. Is that true? How would you explain that to somebody? She says you can't do that.
Because that would put it on the bottom of the, because it's an exponent.
Yeah.
Okay. Yeah.
And
So
negative exponent, small fraction.
can you have, here, let me cover up the 2 here. We don't need to worry about this 2 out front. Can we have an exponent of 2? Think of that. Any number that's the exponent of 2 that's going to give you a negative result? No, 2 to some power that gives you a negative result? No, because 2 to some power is always positive, isn't it?
Yep.
Good. So you can't have logarithms of negative numbers. So right away then we can discard this negative 3.1 answer as what we call in mathematics an extraneous root. Extraneous root. Okay, so the 1.1 answer would check if we stuck that back in the problem originally. Okay, we took a long time on starting out with a log expression and then going ahead and making it into an equation and solving it. Let's go ahead and solve some others now today and get into some applications as well.
It would never happen that you'd have both roots be extraneous, or does that happen sometimes?
I haven't seen that in textbooks.
But in real life,
In the real world, you certainly could get those kind of situations, yeah, where you don't get there is no real answer. That happens back in your basic level algebra background as well, like with the quadratic equation, where sometimes you don't have any real answers coming out. Okay. Let's grab another problem or two right out of the book. So let's say we took a problem like number 42. This is over on page 311. Here's the equation. 2 raised to the x plus 1 equals 5 to the 1 minus 2x. Two raised to the x plus 1 equals 5 to the 1 minus 2x. If we took a little bit of time, we could graphically solve this problem by drawing a picture of this. This is a 2 to the x graph that's had what done to it? 2 to the x shifted to the left 1. So it's a 2 to the x graph shifted to the left 1. So just take, sometimes I will draw a little mini sketch down here. Instead of it having a y-intercept at 1 and rolling on up like a 2 to the x does, it's shifted 1 to the left, so it looks like this. Okay, so that's this left side graph. This right side one's a little more complicated, but it's a transformation. But we're not going to worry about that particular transform. You've learned it, except I'm not going to take the time on it. It's a 5 to the x type of graph that's had something done to it. The intersection of this graph and that graph, which you can do easily on your graphing calculator, the intersection of those two graphs is where the y values are the same. And so you could solve for the intersection from the graphs, the intersection of the two graphs. Okay, but we want to do it by algebra. So let's use, first of all, we have an exponential equation. So first of all, always identify your equation, the type of equation. And so how do you solve exponential equations, unknown exponents here? How do you solve them? No, we can't make these bases. You did some problems like that before where you were able to match bases. But man, we can't break 5 down into an exponent with 2, a base of 2, can we? So we can't do that. So when you see an exponential equation in general, you need to use logarithms to solve it. So you want to use logs to solve it. Because that power rule, once you've got the logarithm, then the power rule is going to let the exponent pop down in front. So we take the logarithm of both sides. Now I want to pick a base that's in my calculator because we want to get an answer when we get done, a numeric answer. So which base do you want to use? ln, base e, or log, which is base 10?
Base 10.
Log? Okay, so base 10 logarithms. So let's just take the log of both sides. Notice how careful I am being with parentheses on those exponents. You want to watch that. Okay, next step, apply the power rule. Apply the power rule, which pops the exponent in front. Now watch this. Parentheses, folks, this is a classic place for a mistake, is forgetting to put the parentheses around that exponent. The reason that's important, the parentheses, in both cases, is because log of 2 is a number. It's just a number. It's the exponent of 10 that gives you 2. Over here, log of 5 is the exponent of 10 that gives you a 5. So they're just numbers, and you can punch them on your calculator. That number has to get multiplied by x and distributed also and multiplied times the 1. Similarly over there, to both terms. That's why you need these parentheses. So now, you look at this equation, and this is a linear equation in the unknown x. So you now distribute. So we have x log of 2 plus the log of 2 equals, distribute over here as well, log of 5 minus 2. You know what I'm going to do? I'm going to write the x first on that last term. minus x times 2 log of 5. Any questions so far? Now you look at this equation, and this is nothing more than like a beginning algebra problem. It's just these numbers are a little fancier here. So what do you do to solve a linear equation with one variable?
Combine like terms.
You combine like terms, which means you just kick the stuff with the x over to one side and move the other stuff to the other side and isolate the x. So I'm going to bring the x terms to the left, so I have x log of 2, bringing this one over. Now watch this. Look at right here for a second. 2 log of 5. What would be an easier way to write 2 log of 5?
22.
Log of
25.
log of 25. Tyler, you see that? Okay, everybody all right? Lauren? Okay. So that's the log of 25 right there. So minus x log of 25 just makes life a little simpler for us. And that's equal to log of 5 here, and then bring this log 2 over to the other side, minus log of 2.
Are we going to add the x log 25 or subtract it back?
Oh, good catch. Ariel caught that. I have a negative on this term, I'm subtracting on this term, so I add this to both sides, so that brings it over as a positive. Good catch. Any questions? We're 99% done with the problem. Factor out the x, and we're left with log 2 plus log 25 equals over here. What's that collapse into, folks? No.
Log of 5
No. Jerome. It's not the log of 3. We're not subtracting the 5 and the 2.
No.
It becomes the log of
5 halves.
5 halves. That's our quotient rule in reverse. With a little bit of practice, you guys can play with these and be pretty good at it. And so then what's your answer going to be here? Oh, look right here also. This is the log of what? Which is log of 50, isn't it? Log of 50 right there. So our answer, our exact answer then, is going to be the log of 5 halves divided by the log of, collapse this into 1, log of 50. Pretty fun. Okay? And so at that point, you can turn on your calculator and get your approximate answer. And I'd like to do that, and then I want to show you how to check a problem like this as well.